right, that was basically as far much I want to say about the mixed feed application and the special consideration of the KR and so on settings in that environment. This is now going on to another special case that we had in one of the questions about the frequency. Is there frequency stability? Then maybe, and I spoke about the inverter in feeds and so on and how we cope with that and deal with that. And let's have a look quickly at the difference here between a conventional on the left and a renewable in feed, and how the protection can deal with that. If we look at this, the conventional in feed on the left-hand side is large turbo generators, typically mechanical rotating objects that have a lot of inertia. That means inertia means you cannot accelerate it very quickly or slowly. It's like a train. You can imagine it's like if you take a bicycle, you can hit the brakes, you can stop in maybe a few meters if you're not going too quickly. But if you have a train cannot, or a big tanker cannot stop immediately. It needs a long time. This is what this is. You cannot immediately stop or make the rotational speed of the generator change. The inertia is there. Not so over here. If we have a static coupled thing, you can see it here, a little bit the diode symbol here, the inverter fed situation, it is static. Also from the name, you can see here it's not static, it is moving. It's a rotational, it's a mechanical in feed, moving in feed, as compared to a static in feed. Static in feed is a solid state electronic in feed as such, thyristors or whatever these modern coupling techniques are. Solar, the wind farms, to a degree, maybe one must be careful. There are different types of wind generators, but I don't want to get into that now. If we look at our two machine model that we used this morning a few times, now we assume that on the left-hand side, we have this mechanical classic in feed with inertia. And then you can say that what do we know? That the voltage is stable. So if there's a fault now going to happen in the line here, the source on the left, the classic in feed, the rotor angle, the blue voltage is not going to jump. We saw that earlier. The motor is going to keep turning at the same speed as before. The frequency is not going to change. The angle is not going to jump. Nothing's going to happen. It is a strong in feed. There will be significant short circuit current in feed. The short circuit current is defined, and we would have clear also sequence components and so on. It's a very, very clear and well understood environment. On the inverter in feed side, it is more difficult, because the inverter needs some algorithm, some software to tell it what to do when the fault happens, but the voltage is going to disappear. There were some cases where you then simply shut down the inverter, said, we don't know what's happening, shut it down. It was a very common technique used in the early days of renewable in feeds to say if the voltage goes away on the network side, the inverter in feed is shut down to wait for the voltage to come back and then reconnect to that. Nowadays, you have certain fault right-through algorithms which define how the inverter in feed does what it does during a fault condition. And there one has to be careful what it's going to do. Why can it be a problem for the protection? We'll have a look at that over here. Okay, clearly on the classic side, it's no problem. The voltage angle is stable. We have defined negative sequence. Remember the sequence components for direction decision and so on. Also for the RMD to determine the load compensation and so on. We need to have a clear definition of that. We have a strong in feed typically. We have stable short circuit currents. The frequency does not change. That means the memory direction criteria is clear. The negative sequence criteria are clear. And we have a stable fault condition. What happens on the static side? It's obviously going to be different. Okay. The voltage angle is not stable. You could, in theory, here jump this voltage angle from one inside a cycle effectively. It doesn't need a cycle. It can jump instantaneously, almost the voltage angle, not quite, but almost. You can define a negative sequence during the fault condition. Need to define what to do. There are certain fault right-through techniques which define now how the negative sequence should look during a fault. So you try and synthesize on this side what a classic in feed would do. That's what one is trying to do now. Weak in feed, you don't have really a short circuit, strong short circuit in feed. It's only really doing active power. There's not really reactive power. Again, fault right-through might define what your power factor or your angle is that you're going to feed during a fault and so on. The frequency may change. Obviously, there's no frequency stability, but there's no inertia in that system. So memory direction, not always okay. Negative sequence, not clear what's going to happen because it depends on how the fault right through is defined. The fault detection, difficult because it's a weak in-feed condition. The criteria change during the fault. This is really not good. It's changing during the fault. So you can see the renewables can create a lot of difficulty for distance protection in theory. So how does one deal with that? We have a solution, CProtect 5, and the CProtect 5 is our the solution for all critical situations. We go to a certain so-called multi-criteria technique. Before I get to that, let's just look at the classic way of doing things. The classic way of doing things was basically with a selection tree. We have got a number of criteria. You can imagine each of these color blocks is different criteria. Maybe the one is a angle criteria, the one might be negative sequence criteria, the one might be a voltage criteria, and so on. Impedance criteria, a lot of criteria, delta criteria, and so on. They're all here. But the interesting thing is here, you come to the selection logic, you look at the first criteria and say, is there the phase current bigger than the ground current, or is ground current large enough? Then you say ground fault or not ground fault, and then you go to other criteria and you end up with a decision down here. The point is you could miss, maybe that light blue criteria might be a very strong, dependable criteria, but you never even reach it because you decided early on that you're going to go down this branch. You never get the information from that light blue criteria. It's a branch or decision tree that you make. Classic way of doing this in a classic Boolean type logic environment. You may know these logic diagrams from old software. It's written like that. It's a technique. What we do now is we apply a multi-criteria technique, which in essence you see on the left-hand side could have the same criteria as the old technique, but they are not in a tree now. They are just evaluated and they give the result with a certain weighting factor into the end result like that. So criteria will never be excluded. Okay, initially all criteria will be able to give their result to the selection logic. So nothing is excluded by the selection path. You give this uncertainty, you give a weighting, something that's called uncertainty here, but I would call it a weighting factor. Say I'm a clear yes, or I'm not sure, somewhere between 0 and 1. You say 0, I have no information. 0.5, say I'm pretty sure. 0.9, I'm very sure that I can tell you what is happening. That's just a weighting factor. It also gives a correct result if situations are difficult. We see some examples in the very extreme conditions. This extracting and evaluating everything in parallel can extract information out of extremely difficult conditions and give you a result which with a plain eye you would not even have been able to see. And important here, it is also suitable for inverter infeeds if we know the control strategy to a certain extent, and that we do know. Because the fault right-through techniques are now defined, and we can deal with those inverter infeeds. It's already implemented, tested, and it's running in the distance protection with the RMD technique is using this for a long time now. From the beginning of the RMD, essentially, it's been using this. It's not new in that sense. So how does it work? You can see all the criteria run in parallel. You can see each criteria here is running to, and then you have a certain weighting here, and then over here you get the 8 loops you can have. Sorry, the 7 loops, the 3-phase to ground loops, the 3-phase to phase loops, and the 3-phase loop. The 3-phase loop, interesting enough, is a separate loop nowadays. In the past, we only had 3-phase to ground loops and 3-phase to phase loops. Now we have got those 6, 3-phase to ground, 3-phase to phase, and the 7th loop, the 3-phase loop. The 3-phase loop is treated as an independent detection. In this example, you see the 10 possible types of fault you can get. Okay, so there are those 7 loops, but the fault combination, you can see the 2-phase can be combined with ground or without ground. The 3-phase we don't consider with or without ground, but the 3-phase to phase loops can be with or without ground. So that takes a 7 and makes 10 out of them, because we have 3 additional fault types: 3-phase to ground, 2-phase to ground, or 2-phase without ground. That's a clear definition there. So in this example, you can see here, for example, would be all the criteria or all the loops get some weighting, but it's clearly in this example complete left-hand side. The L1 to ground has got the highest, by far the biggest magnitude, and the selection would clearly say, yes, it is an L1 to ground fault, because all the others see a little bit. Remember, an L2 to ground would also see some ground criteria. See, it's a ground fault, so it could be L2 to ground, but that's the only thing it has, is some ground current. Nothing else. The voltage and so on would not confirm that, so the L1 would be selected. But we'll see that maybe more effectively in a graphic form just now. Here's one criteria, a voltage magnitude criteria as an example, and you can see, obviously, if the voltage magnitude here is not decaying, remember this would be rated voltage 1, and if the voltage during the fault only drops a little bit, then you would say, okay, I could be a fault, but very small uncertainty, only a very small quality, 0.1 or less. If, however, the voltage drops down to a very small value, all the way down to 25% in this example, from full voltage 1 down to 25% voltage, for example, then it is a strong criteria, and it'll give you a quality almost of 1. To say this phase must be faulted. This is clear. If this is the A phase voltage, then the A phase must be faulted. Otherwise, the voltage on the A phase would not drop to 25%. The voltage criteria is strong. And this would happen during a weak infeed. Remember, if you have a weak infeed, then you have a severe voltage drop. Okay, if you have a strong infeed and it's a little bit remote fault and so on, you could have a smaller voltage drop. So you can see this is an interesting technique over here. Look at the current, it's going to be the opposite. In the current, you can see if the current is a small value close, smaller than rated voltage, 1 would be nominal voltage, then the current is a weak criteria, gives you only 10% quality. But if the current is like here, bigger than 4 times rated current, it's a strong criteria. So this would be the strong infeed. Remember the voltage, it was the opposite. So the criteria complement each other. If the one criteria is good for one network condition, the other criteria might be poor, then it'll be the other way around in a different network condition. So that, and you can see this here, clear fault condition due to the current, strong quality, a weak fault condition. You can see here, the current only goes up, stays at, it was a really small current, but the fact that it went up a little bit, if you did a delta in here, obviously you would see the increase, the delta here would, the delta criteria on the current here would be quite strong, but you get a significant increase of the current. So remember, there are also delta criteria, which I did not explicitly show here, but they also work in parallel, making up the 11 or 12 criteria we have. And here's an example. This is an L1 to ground fault. I think clearly to be seen, you can see the L1 voltage disappears here, and you get current only in L1, and you can see the criteria here, L1 to ground goes up to almost 100%. Clearly in all the other criteria are somewhere down. The loop selection just selects L1 to ground. It was easy as such, okay, to detect that. Other conditions are more difficult. I don't want to go to too many examples now. The same also applies in the area of direction determination, because remember, the direction determination can be affected. For example, the frequency stability was one issue. The angle, the jump of an angle could be a problem for direction criteria. So on the direction, we also do a multi-criteria technique. And you can see there some examples. Self-polarization, it's a self, like remember the self-polarized Mohs circle as an example. The memory polarization to offset the Mohs circle we had. The cross-polarization as an alternative to the memory voltage. And there are other techniques here, delta techniques. Remember we saw the negative sequence or the zero sequence voltages for direction decision. And basically all of those are working in parallel in the same way. And you summate them, and you then would use, based on the weighting factor, you see for each loop you get a decision, okay, it's clearly forward, reverse, unknown, not sure. So it will be a forward decision here because that technique works in parallel with all the others.